All right, so we will continue in our discussion of the neural network as an application of gradient descent. Okay, so we'll say neural network. Okay, and so far our neural network, we have two x's for our input. We have a hidden layer with 3 nodes and an output layer with 1 node. Okay. And we said that we have our inputs, kind of our x's. We have our first weight matrix. And then, and so we multiply these together. And this kind of provides our inputs for the second layer. Okay. And then we apply our activation function, which is the sigmoid. And we will say we're going to define the results of applying the activation function as what happens after we take our Z matrix and apply F to it. Okay. Then we will take A2 and multiply it by our second weight matrix. And this provides kind of the inputs at our third layer. And lastly, we apply the activation function to these values. And this provides our predictions. Okay. And what we want to do is we want to train the network, meaning we want to find out which set of weights work best to produce the appropriate predictions, okay? We want to train our network, so we will use our training data to find the weights that will work best. Okay, and so what we're going to do is we're going to use gradient descent to figure out the weights. Okay, we're going to take gradient descent to figure out the weights. So all of these equations, this is kind of the forward propagation. To train the weights. Okay, so how does gradient descent work? The way we're going to do gradient descent is kind of basically the next set of values. The next set of values, what do we do to get our next set of values? We take our current set of values and then we subtract lambda times the gradient, exactly, of our current set of values. Okay, so the gradient here is effectively the derivative of our loss function, right? Okay, so again, we have our loss function, which is effectively going to be the sum of squared residuals. Okay, and so we can say L is the sum of basically y minus y hat squared, and just to get rid of this 2 later, we're going to just multiply it by 1/2. This 1/2 is just kind of artificially inserted. To get rid of the 2 later. Okay, so multiplying this by a constant, the loss function is not going to change where the minimum is, right? So multiplying where the minimum is, so it's okay that we do this. I think in one of your homework exercises you're multiplying it, or you're getting rid of 1/n. You're multiplying it by n or something. The exercise basically shows that it's not going to change where you find the minimum. Okay. Okay, so this is our loss function. I will provide some links to videos that follow kind of exactly what I'm doing here very closely, except in the videos they use the letter J for the loss function. Okay, so I'll just say in video they use J for the loss function. So, but don't be confused. Okay, so this is our loss function. We want to differentiate the loss function, okay, with respect to W, and we have 2 W's, so we're going to have to figure out 2 different derivatives effectively, okay? So we have 2 W matrices. Okay. So we will have to figure out gradient for each matrix. Okay, and so when we think about this, okay, we have our first weight matrix. What are the dimensions of the first weight matrix, and what are the dimensions of the second weight matrix? So the dimensions of the first, this covers the going from our 2 inputs to our 3 nodes, right? So So this is the W. So this matrix is going to be what? 2 by 3. Okay. So when I take the derivative of the loss with respect to W, what's the dimension of that going to be? It will also be 2 by 3. Okay. So derivative of the loss with respect to W1 will also be 2 by 3, right? Because we have to be able to combine them, right? We're going to take this and we're going to subtract off this, so they have to be the same dimensions. Otherwise, we can't subtract off the gradient from our current values. Is that okay? We got 2 inputs and 3 outputs, so it's a 2 by 3 matrix. Okay, the second weight matrix, which takes our 3 outputs, or I mean our 3 from our hidden layer and goes to our 1 output. How many, what are the dimensions of this one? Three by 1, okay? It's taking 3 in and it's putting 1 out, okay? And so the gradient of dW2 will be 3 by 1. Okay, and so this is, we're going to take the gradient here, or take the derivatives with respect to W2 and W1, and this is where back propagation happens. Okay, we're just seeing how the final, our loss function, okay, how that is affected by everything going through the matrix, or going through the network. Okay, so if I may flip the page here, that's what we'll do. Okay, so because W2 is closer to the end, we will find W2 first. Okay, we will find derivative of the loss with respect to W2 first. Okay, so we want derivative of the loss with respect to W2. So this is the derivative with respect to W2 of the sum of squared so what we're going to do, okay? And the derivative of a sum is just the sum of the derivatives, so this is just going to be the sum of each of these things. Okay, and then we can figure out the sum later. Okay. Okay, so this is we'll find this first. Okay, so when we take the derivative of this, we'll bring the 2 down. Okay, so if we think about how these things vary with respect to W, okay, so we're going to say y does not vary. Y is our the output, the y values in our data, right? So y is our data. So y does not vary with respect to W2. Okay, so we don't have to worry about that. Okay, so but y hat is, right, our predictions very much depend on the weight matrix W2. Okay, y is our data, y does not, okay, but y hat are our predictions. They depend on W2. Okay, so when we take this derivative here, we're going to just do this. We're going to multiply the 2 times the 1/2, and we get y minus y hat there. And then we have to apply the chain rule, so we're going to have a -1 times derivative of y hat with respect to W2. Okay, so this so all of this just becomes negative y minus y hat dy hat with respect to W2. Okay. Now if we think about what is y hat, how did we get our y hats? Okay. So I'll just say recall y hat is equal to applying our sigmoid function f to the Z3 matrix. Okay. Is everything okay? Are there questions so far? We're okay so far? Okay. All right, and so recall that y hat is this, and f of just a single value is 1 over 1 plus e to the negative z. Okay, and so the derivative of f prime of z, okay, if we, do a, what is it, quotient rule? U over v is u prime v minus uv prime over v squared. Okay, and so, when we do this, we get e to the negative z over 1 plus e to the negative z. That's a z. E to the negative z squared. Okay, so we'll just say this is f prime of z here. So what I can do is I can say, well, what is y hat? We can split this. To dy hat with respect to z3, and then dz3 with respect to W2, right? So we can do it this way, and the derivative of y hat with respect to z3 is going to be our f prime of z3. Okay, so this becomes negative y minus y hat times f prime of our Z matrix and we're going to find the derivative of Z3 with respect to W2. Are we doing okay? Okay, and then so now we're going to find Z3 with respect to W2. Okay, so let's see. Can I fit this on the screen? Maybe not. I'm going to go ahead and copy this onto the next slide. Okay, so we want to find how does Z3 vary with respect to the W2 matrix. Okay, So if you recall our neural network, we go from here to here, right? Okay. The z's is kind of what we're outputting, all right? And then we multiply it by the W2 values. Okay. So, I'm sorry, not the z's aren't there. The z's are what get input into this stuff here. Okay. So what is combining with W2 to make our Z3? Okay. So earlier we established that Z3 is what's coming out of our A2s after applying the activations to this hidden layer. In there. So, f prime of Z3, and this becomes just our A2 matrix, okay, effectively. All right, and this is where everything, so we're going to do something a little bit funny here and put it into matrix notation to handle back kind of the sum, right? So often when you multiply by matrices, you multiply and then you add things up, right? So let's just recall what are the dimensions of each of these things. What are the dimensions of y minus y hat? Or what's the dimensions of y? It's, yeah, n by 1, right? So y is equal to n by 1. And in our example, we have 3 training examples, right? So n equals to the number of training examples. Okay. So here, this one is a kind of a n by 1. And then if we look at our Z3, what are the dimensions there? This is also n by 1, okay? And this works by doing element-wise multiplication. Z3 is n by 1, and f prime of Z3 is also n by 1.
Isn't that a multiplication instrument? N by 1 times n by 1, or is it plus by n?
It's n by 1 and n by 1. We're not we're doing element-wise multiplication. We're not doing matrix multiplication. We're saying the first element goes by the first element, the second element goes by the second element, the nth element goes with the nth element. Okay, so this is element-wise multiplication here. Okay, and then this, we want to kind of include this A thing. This is going to be a n by 3. Okay. So we have, because we have 3 nodes, right? So this is n elements and 3 nodes. And so what we can do to handle this, okay, just because this is going to get messy here, to take care of it, we can transpose this A thing, okay? So if I take A2 transpose, okay, now we have a 3 by n, and then I can multiply this by y minus y hat and f prime of Z3. And this stuff, after it's multiplied, is still n by 1. Okay, and so the resulting matrix here will be a 3 by 1 matrix. Yes. Oh, I left it off. Okay, and so we can call this thing, we can call the product of all of this stuff together, we can call this delta, okay, and we'll give it delta 3, and we'll say we're multiplying it by A2 transpose. Okay, so this is the derivative of our loss function with respect to our matrix. And again, this is a 3 by n matrix after being transposed, and this is n by 1. And so the resulting matrix is our gradient with respect to W2 is a 3 by 1 matrix, okay, which is what we want. Okay, so over here we define delta 3 equal to minus y hat f prime z3. Is that okay? Okay, so we can continue this, but we want to let's now we want to find the gradient with respect to W1, okay? And so if we think about this, kind of the many of the steps of the above go through until we kind of get to this last step. So I'm going to just kind of say we're going to same steps as before, same steps as what we did for W2, okay, until we get to, and I'll say we are at here y minus y hat f prime of z3, and now we want to find how z3 varies with respect to W1. Okay, so the rest of the stuff is the same up to here, and we just now, instead of finding how Z3 varies with respect to W2, which we said was the A matrix, we're going to say it's Z3 with respect to W1. Okay, and we have already defined this. Okay, this is saved already as delta 3. Okay. So now I have delta 3, and we want, how does Z3 vary with respect to the W1 matrix, okay? And so I'm going to actually split this up from the W1 matrix, we're going to say it varies with respect to A2, and then we're going to find the derivative of A2 with respect to W1. Okay. So if we think of how does Z3 vary with respect to A2, this is our W2 matrix, okay? And with the way the multiplication works out, delta we established to be n by 1, and W2 is going to be 3 by 1. So for the multiplication to work out, we're going to transpose this, and we're going to have a 1 by 3. Okay, and now we're going to have this A2 with respect to W1. Now, A2 we're going to further split into A2 with respect to Z2, and then Z2 with respect to W1. So we just keep applying the chain rule here. Just keep that thing splits into that derivative with respect to that, and then the derivative with respect there. Okay? And so again, you know, if we think about what is A2, A2 is the application of the sigmoid function to Z2. So dA2 dz Z2 is just f prime of Z2. All right. So this here is f prime Z2, and then we've got d Z2 dW1. Okay, and this is n by 1, this is 1 by 3, and then f prime of Z2, let me think about this, Z2 is a 3 by 3, I'm sorry, is a n by 3, okay, and so this part is element-wise, okay, so n by 1 gets multiplied by 1 by 3, this and this combine to n by 3, and then over here we have n by 3, this part is element-wise. Element multiplication. Okay, and then, so lastly, we just have to take care of this last term. dZ2 with respect to W1, this is, if we look at how we calculated Z2, we said Z2 is equal to X times W1. So we want this. Z2 is n by 3, X is, no wait, Z2, yeah, is n by 3. X is n by 2, and W is 2 by 3, okay? And so we want to say this is going to become X, effectively X, but in order for the things to line up, we're going to transpose this and put it in the beginning, okay? So we transpose the X, and this will give us a 2 by n, and then we can multiply this by delta 3, which is n by 1 multiplied by W2 transpose, which is 1 by 3. So these combine to an n by 3 matrix, and then we have element-wise multiplication for f prime of Z2, which is n by 3. So this is standard regular multiplication, and then regular matrix multiplication. This part here is element. So these get element multiplied, and we get the resulting will be a 2 by 3 matrix. So this is X transpose delta 3 with respect W2 transpose F prime Z2. Okay. Is this okay? So we've derived what the gradients are with respect to W1 and W2. And so now we just code this up in R, okay? The easy part. Okay, and so I've written the code for you, and it's posted online, and I'll walk you through what we're doing here, okay? All right. So when you open up that file, I'm just setting up our data here, okay? So we have our X matrix. Oops. So our X matrix is currently 3 by 2. And then our Y is a 3 by 1. Okay, this is our output. And one thing about the neural network is that it works best if you scale everything on 0 to 1s. Okay, so you put everything on a 0 to 1 scale just because, well, there's a lot of reasons, but it works better a lot of times when you just kind of scale things from 0 to 1. So that's what we're going to do. We're going to just take each of our X values and divide them by the column max. Okay, and then so my X, whoops, X is, did that not work? Oh, so now I've scaled these on from 0 to 1, and then cap Y, we're just going to divide everything over here. So our inputs are on a scale from 0 to 1, and our outputs are also on a scale from 0 to 1. Okay. We're in the, instead of using actual numbers, say we have 2 in our input layer and 1 in our output layer and 3 in our hidden layer, we're going to just use variables. And that way you can kind of, if you need to modify your network, you can reuse the same code and just change the numbers here rather than searching for every 2 and every 1 and every 3, okay? Okay, so our weight matrix, right now I'm just creating a blank, not a blank matrix, but it's just filled with 1s right now. Where's my, okay, and then we'll do the same thing. We're going to say Z is, my keyboard just died. Oh man. Okay, no, it's working. Okay, and then we're going to take x multiplied by w1 is z. We're going to say our sigmoid is, we're going to take the function, apply the function, okay? And the way R works with the functions is this is element-wise, so whatever dimensions z is, so z2 is 3 by 3, and then so if I do sigmoid of z2, it just applies it element-wise, so that's perfect, okay? And then you know, here's a, and then we can say that we're going to take our second weight matrix, which is 3 by 1, and we say A2 multiplied by our second weight matrix is going to be our Z3, and we have y hat is the sigmoid of this, okay? Our cost function, this is, or our loss function or cost function is what we are trying to optimize, and we can say currently this is our current cost and current loss, and we want to minimize this. So we're going to calculate all of these derivatives, okay? So we got, you know, we want derivative with respect to W2, which is kind of in loose terms is this. We've defined that, and so we have f prime sigmoid prime we've written up as, you know, e to the negative z, 1 plus e to the negative z squared. And sorry, here I'm using the same notation as the video. So rather than L for loss, it's J here, okay? But we've defined delta 3 as y minus y hat, negative y minus y hat times, so notice this is the regular element-wise multiplication versus the matrix multiplication, which is the so percent star percent is matrix multiplication, and then regular old star is element-wise multiplication. I think I have to unplug my tablet here. Okay, so we have this, so we've defined delta 3 as that, and then we said the derivative with respect to W2 is going to be the transpose of A2 and delta 3. So we've defined that. And then we go further on and we say delta 3 times the transpose of W2 times f prime of z, which is what we have here, is that, and we do the matrix multiplication by the transpose of x, and this is going to be exactly what we have here, the loss function with respect to W1. Okay, so here I've coded up, and these are the respective gradients for our W1 and W2 matrices, and that's great. And I guess we're out of time, but we can do the gradient descent. All we have to do is we take our current estimates of W1 and subtract off the scalar, our lambda, multiplied by our gradient. Okay, and we can do this. And I guess on Wednesday we'll look through the rest of this and work it out here. Okay.